So, before I start, I want to ask all of you, do you trust your computer? Do you trust that it's always computing the right thing? Then the question is, what do we mean by right thing, and what is a computer? So, things happen. This poor fellow that owns this house probably have an insurance issue after this. It's kind of interesting to see how this actually happened. But did you know that the modern car has more than 80 computers, embedded computers inside itself? So when you're steering your car, you're not actually steering the car, you're communicating with a computer that is steering the car. And these kind of systems are developed by human beings. But we are not the only ones that are going to drive these things in the future. So, self-driving cars are not just a vision anymore. It's coming here, and it's coming fast. And one thing we know is that human beings and machines, we do make mistakes. So, areas that we're interested in here are, for example, automotive, industrial automation, aircrafts, satellites. We have one project with students where we're creating a small miniature satellite that will be launched in a couple of years, and medical equipment. So a term that is used for these kind of systems is cyber-physical systems. I don't know how many of you have heard about it, but it's been around. It's actually from the 60s, but now used the last, say, 10 years, especially in academia. Maybe a way to get new funding opportunities. But it's some interesting part here. It's emphasized the relation between the cyber and the physics. So the cyber would be the computational part and the physical dynamics. That is the problem. And the real interesting thing is how these things intersect. Because there are different communities working on different problems of these very complex systems. So, on this kind of system, you have a physical plant. And you have embedded systems, typically embedded, and they can be connected into networks. To make them work, you have sensors, sensing information from the physical part, and you have actuators that are controlling the systems. So these systems can be extremely complex. And how do we manage all this complexity in systems? Okay, what is this? It's a subway map of Stockholm. Pretty old one, I guess. So, if we look at this part here, we have Kista now, and this is the distance to Åkeshov, another place in Stockholm. And here is the distance between Kungsträdgården and Odenplan. If we look at another map here, we see that this is the distance between Kista and Åkeshov, and this is the distance between Kungsträdgården and Odenplan. So what do I want to say about this? So this is typically how I introduce the idea of models to my students. So what is a model? Model is an abstraction. So a map is an abstraction. But typically, there's not just one abstraction. You want to have different kinds of abstractions for solving different problems. You see here, this map abstracts away a lot about actually the depth of the water, but it shows the physical location, the distance, in a correct way. Whereas here, we're just interested in the connection points between different stations. So the distance here is really incorrect, but that's not what the model is trying to show. So the same thing, when we try to develop these kind of complex systems, we don't have one model. We need to have many models. We want to have heterogeneous models describing different parts of the systems in different ways. So we develop the systems by making abstractions. And if you look at the side on the cyber part, so the embedded systems, networks, and so forth, we have different models of computations or formalisms, which can be described in different so-called domain-specific languages. Languages that are tailored for different properties. What about this side? What kind of models do you have on the physical part? Of course, you can have CAD models describing the actual physical constraints on properties. But if you want to study these kind of systems, you often are interested in the dynamic models. So if you ask a control engineer, what is a model? He will not answer UML. he will say differential equations, typically describing the physical dynamics of the system. And there are many different languages that are used for, and particularly good at describing these kind of systems. And I've been involved in one language that is now being pretty big deal in industry. It's called Modelica, where you can express differential equations in a manner as you do in a textbook, basically. So if you have both these models, you have models of the physical part and the cyber part, you can of course do simulations. You can study the physical dynamics, you can test drive the car without having the car. So you can do some sort of virtual testing. Sometimes when you're developing this system, you have these parts here, but you don't have the physical part. Could be that some other organization is actually developing this. Could be that it's too expensive to have a landing gear here located in your facilities when you're developing the controller. So then what you can do if you have the physical model is to do what's called hardware-in-the-loop simulation. So you're simulating the physical plant in real time while running this part. So of course, one of the challenges here is to do this in real time. So then you have your computational problem, to be able to perform the simulation in real time. These kind of models can have hundreds of thousands of differential equations. So it can be very complex. Okay, so of course you want to go in the other direction as well. You need to go down. If you go abstract, you want to become more concrete. You want to refine the models. So going here, you have to basically build physical prototypes. So this is what you always have to do. But the idea of doing computational models is to reduce the number of physical prototypes that you have to do. So you save money, basically. And also you can do experiments that are harder to do that is hard to do with a physical prototype. You also want to go in that direction, of course, here as well. Unfortunately, that is not done as much as we want to. One thing is, of course, you have abstracted away a lot of information, but it's also not that easy to go in that direction, because it's not only concerns the functionality of the models, you also have non-functional requirements to handle, for example, timing properties, and to do that right in the physical system. So in our group, we're looking at a couple of different main research challenges, as you can say it. So one part is about how do we define domain-specific languages, languages tailored for different formalisms, in a way that we can have them, they are expressive enough, and that we can analyze properties of the languages. And that they also are extensible, so you can have one language and extend it to create new languages. And I say that one of the main challenge here is this heterogeneous landscape, that you have a multitude of different formalisms. How do they interconnect? So some work we have done there is called on something called the FMI, functional mockup interface. It's also standard for doing hybrid co-simulation. Another part is, of course, if you want to go down and compile or synthesize, you want to have high performance compilation of systems that still fulfills real-time constraints. I would say some of the main challenges here are this handling of time. How do we express time? How do we verify timing properties when we have a flow of both, say, soft and hard real-time systems? Sometimes called also that we have mixed criticality systems. Another thing is that we don't have just one type of platform, hardware platform anymore. We have basically a heterogeneous landscape of platforms as well, especially if you want to do high-performance computing. We have CPUs with several cores. We have different memory hierarchies optimized for different cache systems. We have GPUs. We have other kinds of accelerators coming. So how do we automate this? I mean, it's very nice with a lot of hardware, but how do we actually program these systems in a simple and systematic way? Going from these high-level models where we describe the properties and then to do this automatically. So these are some of the questions that we think are very interesting. So in the rest of the talk, I'm going to talk a little bit about one effort. It's called Modelize. It's about heterogeneous modeling. And then I'm also going to say a few words about an ongoing project called Time C. It's about programming with time. So our approach to this heterogeneous modeling is to do embedded domain-specific languages. So how many of you, hands up, have heard of embedded DSLs? Maybe 20%, 20, 30%. Okay, so this effort Modelize is basically a host language, so it's a general purpose language, but it's a host language designed for embedding DSLs. So first of all, what is a DSL? Well, it's a domain-specific language. What does that mean? Well, it's tailored for some specific domain, in contrast to a general purpose language. But of course, general purpose languages are not really that general. They're also tailored for certain domains as well. It's just the different levels of how domain-specific you are. Okay, so when you develop these kind of domain-specific languages, one way is to basically do it from scratch. You have to have a syntax, and you have the semantics. And they both start on S. So that's why we have different colors. You have syntax and semantics for each of these languages. And of course, you can go ahead and write your own parser, define your type system, write a compiler, generate efficient code for each of these languages. But it's a big, big job to do, especially if the domain-specific language that is not going to be used by like a very large community. It could be just too expensive. So this is called the external DSL approach, that you basically write new languages, new compilers for specific domains. An alternative is that you have a host language which is basically a general purpose language. And the general purpose language has got a syntax and a semantics, of course, and might have more than one compiler for this language. And then, instead of creating new DSLs, you embed the DSLs into the host language. So basically, you write the programs, the language as libraries. The challenge is to make it feel, when you're using these DSLs, as it is a DSL, and it's not the host language. So popular languages for embedding is, for example, Haskell or Scala. Spark, for example, can be seen as a kind of DSL in Scala. So challenges are one thing to get the feeling, but it's also about getting the right error messages. People are using templates in C++ to do this. Can look nice, but when you get this enormous amount of template error messages, it can be hard to understand what that actually means, because it's kind of the host language information are pushed back to the end user of DSL. So these are the challenges when you are embedding DSLs. So what we are doing here is basically we try to develop a host language, which is a general purpose language, but it's designed for embedding. So it's really designed to make it easy to embed DSLs and also get the nice properties of getting good error messages and also get a good runtime system for free. So that is the overall goal of this work. Okay, so if we look at an example here. So previously we've been mostly working on the domain of equation-based DSLs for this modeling part. We've also been looking at synchronous languages for real-time programming. And now we have a pretty big project on probabilistic models. So we are going to incorporate probabilistic models combined with inference algorithms. So basically to make it easier to do complex machine learning algorithms for CPS. But this example is a equation-based language. So if you're a control engineer, you can, for example, model this using two variables here. You have x and y direction, modeling this pendulum that will swing. So you have Newton's law in x and y direction if you do this in Cartesian coordinates. And then we have this is called an algebraic constraint, as you see here. It basically specifies that the pendulum will always go in this trajectory. So you declare to describe this, and you want to study the behavior. So this is how you could write it in a textbook. And then as a domain expert or a domain user, you basically do not want to write a Runge-Kutta solver to be able to solve this. You just want to express the equations and study the behavior. So if you will do this in a DSL that is defined in modelize, it could look like this. So you have a pendulum with some parameters. You define your variables. You have your initial conditions, which corresponds to these ones. And you have your equations. And as you can see, the equations directly corresponds to the math here. So you have this y prime prime corresponds to the second order derivative of y. So if you remember your calculus from school. So the point is here that these are equations. So you can change the order. It has the same meaning. You can manipulate algebraically as long as you're following the normal rules, will give the same result. So it's a model described in the domain of this particular domain. So then the question, what part is part of the host language? And it's actually only this part. So the way how you define a function in this case. But this is used also as the abstraction of this model. In this case, we call that model a pendulum. And the second part here, the way to be able to define typed symbols. So you see here, these are actually unknowns. We define them, but we do not give them a value. Okay, so what is the rest then? Well, the rest is defined using libraries. So you extend the syntax in libraries, and you define the semantics, the meaning of these equations. So modelize, the host language do not know anything about equations, anything about differential equations. Instead, this is defined by transformations, symbolic transformations, and in the end, to be able to produce a simulation result, it's using classic numerical solving techniques. So different ODE solvers, basically. Okay, so but the point is to separate these from the end user. So how is this working? What is the process here? So if you see here, you can talk about the static semantics. This would be the thing that happens at compile time. And the dynamic semantics, basically executed and runtime. And if it's a compiled process, the runtime is after the program is compiled and then executed. And then of course, this becomes a little bit more blurred when you talk about JIT compilers and so on. So in this case, you have as input the model, which is basically a program. But for the domain user, it's differential equations. It's a model. Then that it's actually a program, and then the domain user doesn't care or know about. To make it expressive, you cannot just add equations, but you have to have model libraries. So we have libraries defined in modelize that describe, standard components in an electrical domain, in the mechanical domain. So you can basically plug these things together and reuse code. So you don't write the equations all the time. You just use components. And then we have as input also the definition of the DSL itself, the semantics of the DSL. This is gone together to the compiler. And the first part is a type checking, which goes hands in hand in something called symbol lifting analysis. And here, by using the types, it figures out what can actually be executed in runtime and what cannot be executed in runtime. So it's lifting things into symbolic expression that cannot be executed. And this means when the program is evaluated, that things that can be executed, for example, if we are using in this case the functions to compose different models together, these ones are executed and collapsed. And then in the end, we have an equation system. Because the equation system, the unknowns were things, when we apply things to the unknowns, are parts that cannot be executed. In this way, we get an equation system, a symbolic representation, that we have functions later on that can operate on these expressions. And in this case, the semantics needs to do symbolic derivation of the system, apply different algorithms before the actual simulation can take place. And then this is interpreted. In this case, right now it's interpreted, but it can also be compiled. And we also apply techniques called partial evaluation, where you basically can transform an interpreter into a compiler by specializing parts of the program. So this part here, that we're transforming symbolic expressions, basically ASTs, is often referred to in the embedded DSL domain as deep embedding, because we are really creating a syntax tree and we're manipulating this. And in the end, we're typically interpreting this AST. Another part that is often, when you divide what kind of embedded DSLs you have, we talk about shallow embedding. Then you're not creating this AST, but rather you're using functions and types as part of the DSL, but it still feels like it's a new DSL. It's a little bit more convenient, and also when you go to deep embedding, that's often when you run into the problems of getting very good error messages, for example. But often you want to combine this, and this is what we are doing in these example DSLs, to combine both shallow and deep embedding. So what we call things, if we're combining shallow and deep, sheep, maybe, sheep embedding. Well, let's put these poor animals out of the picture and mispronounce this a little bit. Maybe we can talk about cheap embedding instead. So the point of making it easy to combine this convenience of shallow embedding and deep embedding and get a bit of both worlds. So there are, of course, other names and so on for this. So it's a general thing that people want to combine these different ways of embedding languages. Okay, so we've talked about, modeling at a high level of heterogeneous systems. But what are our goals actually here in these kind of systems? In these, general complex cyber-physical systems, and trying to find methodologies how to develop these systems in a more systematic and better way. Everything should be made as simple as possible, but not simpler. Who said that? Yeah, at least it's attributed to this smart guy. Execution time should be as short as possible, but not shorter. Who said that? I just did. Okay, so what do I mean by that? So if you look at this kind of system where you have the cyber part where you're executing things in the real-time system, you typically have different tasks that have to execute, and you have some deadlines. These deadlines could be hard or soft. It could mean that you have to meet the deadline, but sometimes it's okay if you miss it sometimes, and we still have some utilization of the deadline, of the computation, even if we miss the deadline. That's called a soft deadline. So, but it's really no point of making things just go faster if you can meet the deadline, of course. It's like, if you try to catch the bus. It's no point of running really, really fast and come to the bus station 20 minutes before time and then just sit there and wait and do nothing. It might be better to relax, save some energy, walk a little bit slower, or stay at home and do something else in between. Often you have many concurrent tasks. So if you look at from that perspective, you also want to optimize other things than the execution time. Typically in this domain, you're not really interested in the average execution time that you are in normal computation. You're interested in the worst case that can happen. So you want to minimize the slack, and you can do this by, for example, if you do this on FPGAs, you maybe want to minimize the area, the memory footprint, because you have constraints on this kind of systems. You can maybe select a cheaper hardware, or you want to optimize for energy. So there is also sometimes a trade-off between performance and energy. But still, if you're working on this kind of systems, you want to meet the deadline. You want to satisfy the timing constraint. So what are these timing constraints? How do you express them? Well, the traditional approach when you program the systems, one thing is that you have these high-level models, but in most cases, in the end, people or someone is developing this in a low-level language, typically C, because C is portable, and if there is a compiler for some embedded system, there will be a C compiler. So you implement the system in your program model, but then when it comes to the timing aspect, it's basically like a consequence of the platform that you're compiling into. Which real-time operating system you're using, what kind of properties the scheduler can give, and so forth. If you're in bare metal, you have to care about interrupts handling, synchronization, and so forth. Just the timing property comes like a consequence when you're compiling. It's not part of the model. So the timing properties are typically not part of the programming model. We don't care about time in the programming model in a classic way. There are a few exceptions. So Ada, for example, have some properties where you describe timing constraints, particularly soft and firm. So what we try to do here in another project, where we talk about programming with time, is to introduce few simple primitives in a low-level language. So you can talk about and reason about time, timeliness, how to handle if you miss deadlines, what do you do? So it's not just if you miss or trying to guarantee that you cannot miss. It's also about how do you react to a missed deadline. Should you interrupt directly when you miss the deadline? It's called a firm task. Or should you run over and then see how much you ran over and maybe get synchronized again? Depending on if you have a distributed system, you might be able to, you want to be synchronized over time on different platforms. So you want to express and reason about time in your programming language. And the reason for doing this is, one, simplicity. It's really hard to program this kind of system. It requires a lot of code if you, for example, use the POSIX API today. But also portability, so that in the best of all worlds, you can really compile into different and target different systems, but have the same source programming language. So I'm almost at the end. So here, we're aiming to target both high-performance compilers or runtime systems, like using modern RTA systems, and also small, cheap nodes where you, for example, let's say sensor network nodes, where you have very limited processing power and where you care about energy. And then that you express the programs, we call it time C, so basically C language, extended with these few programming language constructs, and then to do source-to-source transformation. So you compile from C with these extra features into C again, but with new constructs. For example, if you compile into POSIX, it will generate POSIX code to be able to handle. If you compile to bare metal, it will generate interrupts handling routines. But the point is that you have the same source language, so you can compile into different systems. If you're interested in hard real time, you also need to go have a feedback loop here to do timing analysis on the hardware to get the information, propagate the information back. This can also be viewed both as programming language, but also as an intermediate language, which you actually compile into. So many high-level modeling languages are used what they call code generators. So they generate C code. It's not about the back end of a compiler code generation, but rather a high-level code generation. So this can also be viewed as an intermediate language for code generation. Okay, so to conclude, I talked about different aspects of CPS and Modelize, which is basically a host language. So it's not a language itself that should be used off the shelf. It's rather for embedding other languages. And also about this fairly new research effort we're doing on time C. Okay, and if you want to know more, you can go to our website for the group. Thank you.
We have time for a question. Just, I will repeat your question.
Okay, so how do you deal with numeric problems in a language like Modelize? I mean, you present a very high-level perspective to the programmer, but then you might do some algebraic transformation that might deal with numeric problems. Do you deal with it in a special way?
So how do you do with numerical aspects of your models in Modelize?
So numerical aspect is always hard when you do simulation of these kind of systems, and it both concerns how you define the semantics of the transformational semantics into an ODE. So like always, there are different algorithm methods that you have to be very careful when you implement this. So it's not off the shelf. Modelize doesn't help you. It's a tool, a language where you implement this. The other aspect is also that there are different numerical solvers that are better or worse for different kind of models. So in this way, you can have as an user input to actually specify other parameters for the solver, which kind of solver you're using. So in the best of all worlds, it will just be you have the model and a push button, and that works in many cases. But as always, if the user wants to have more control, you need to give this control back.
So let's have a break, and please be back on time. It's only a 15-minute break, so it's not that generous. I'm really, really, nasty. So, and let's thank David again.